Imagine a man standing alone in an endless, flat world. His name is Mr. Victor. He has no map, no compass, only a direction he believes in and a distance he's willing to walk. He looks out toward the horizon. Something in him says, 2 steps east, 1 step north. That's who he is. That's his entire identity, a direction and a commitment. He doesn't wander. He doesn't curve. When Mr. Victor moves, he moves in a perfectly straight line from where he began. And where did he begin? At a place everyone in this world calls home. The origin, the still point from which all journeys are measured. In linear algebra, Mr. Victor is a vector. A vector has 2 pieces of information, a direction and a magnitude. We write Mr. Victor as v equals the vector 2, 1. The first component, 2, tells us how far he travels in the horizontal direction, the x-axis. The second component, 1, tells us how far he travels in the vertical direction, the y-axis. We draw him as an arrow, starting from the origin, the point 0, 0, and ending at the point 2, 1. Now imagine Mr. Victor is not alone. Across the flat expanse, another traveler stands at the origin. Her name is Mrs. Willa. She has her own direction, her own conviction. Where Mr. Victor walks east and slightly north, Mrs. Willa walks east and slightly south. She looks at the horizon and thinks, 2 steps east, 1 step south. That's her path. That's who she is. They don't argue about whose direction is right. They simply are who they are. 2 travelers standing at the same starting point, facing different futures. Mrs. Willa is also a vector. We write her as w equals the vector 2, negative 1. Her first component is 2. She also moves 2 units in the x direction. But her second component is negative 1, meaning she moves 1 unit in the negative y direction. When we draw both vectors from the origin, we see 2 arrows pointing in different directions. They are not the same. They are independent. One morning, 2 mysterious figures appear at the origin. The first is Sir Constant. He approaches Mr. Victor and says, "I can change how far you go without changing who you are. Tell me a number, and I'll stretch you or shrink you by exactly that much." The second is Dame Della. She walks toward Mrs. Willa with the same offer. These are the transformers. They don't travel themselves. They amplify or diminish the travelers they touch. Imagine Sir Constant chooses the number 3. He places his hand on Mr. Victor's shoulder. Suddenly, Mr. Victor's journey isn't 2 east and 1 north anymore. It's 6 east and 3 north. 3 times the man he was. Same direction, greater reach. Now imagine Sir Constant chooses a different number, negative 1. This is the power of Mr. Minus. When Mr. Minus touches a traveler, he doesn't change their strength, only their direction. Everything flips. Forward becomes backward. Mr. Victor, who once walked east and north, now walks west and south. Same road, opposite direction. And imagine Sir Constant chooses 1/2. This is Madame Moitier's gift. She asks travelers to hold back, to go only halfway. Mr. Victor's journey becomes just 1 east and 1/2 step north. Tempered, restrained, but still himself. Sir Constant is a scalar, a single number that multiplies a vector. When we multiply v by the scalar c equals 3, we get 3v equals 3 times the vector 2, 1, which equals the vector 6, 3. Each component is multiplied by 3. The direction stays the same. The magnitude, the length of the arrow, triples. When we multiply by -1, -1 times v equals -v, which equals the vector -2, -1. The vector reverses direction but keeps the same length. When we multiply by 1/2 times v equals the vector 1, 0.5. The vector shrinks to half its original length. This operation is called scalar multiplication. Now imagine something remarkable. Sir Constant transforms Mr. Victor. Dame Della transforms Mrs. Willa. And then, the two transformed travelers combine their journeys. Here is how it works. Mr. Victor walks his transformed path. When he stops, when he plants his feet at his new position, Mrs. Willa begins. She starts from where Victor ended, and she walks her own transformed path. Where do they arrive? Somewhere neither could have reached alone. Imagine Sir Constant chooses 5. Mr. Victor walks 5 times his usual journey, 10 steps east, 5 steps north. Now imagine Dame Della chooses -2. Mrs. Willa turns around, Mr. Minus's influence, and walks twice her usual distance in the opposite direction. That's 4 steps west and 2 steps north. Mr. Victor arrives at 10.5. Mrs. Willa, starting from there, walks -4.2. Together, they end at 6.7. This is collaboration. This is what happens when two travelers, each shaped by their own transformer, join forces. This is called a linear combination. If Sir Constant is the scalar c and Dame Della is the scalar d, then the linear combination of v and w is c times v plus d times w. For the example where c equals 5 and d equals -2, 5v minus 2w equals 5 times the vector 2, 1 minus 2 times the vector 2, -1. This equals the vector 10, 5 minus the vector 4, -2, which equals the vector 6, 7. The result is a new vector, a new destination. Linear combinations are built from two operations: scalar multiplication and vector addition. Multiply each vector by its scalar, then add the results. Before we speak of possibility, let us speak of limitation. Imagine Mr. Victor stands at the origin, ready to walk his path, 2 steps east, 1 step north. Now imagine another traveler appears beside him. His name is Mr. Shadow. Mr. Shadow looks at Mr. Victor with admiration. He studies Victor's direction, and when it comes time to choose his own path, he doesn't look to the horizon and ask himself what he believes. Instead, he copies. He says, "I'll walk the same direction as Mr. Victor. Perhaps I'll go farther. 6 steps east, 3 steps north, but I'll stay on his road." Now Sir Constant approaches Mr. Victor. Dame Della approaches Mr. Shadow. They each choose a number. They transform the travelers. And the two transformed travelers combine their journeys, one after the other. Where can they reach? Imagine Sir Constant chooses 2. Mr. Victor walks twice his usual distance, 4 steps east, 2 steps north. Then Dame Della chooses 1. Mr. Shadow walks his full distance, 6 steps east, 3 steps north. Combined, they arrive at 10 steps east, 5 steps north. Now imagine different numbers. Sir Constant chooses -1. Mr. Victor turns around and walks backward, 2 steps west, 1 step south. Dame Della chooses 3. Mr. Shadow walks 3 times his distance, 18 steps east, 9 steps north. Combined, they arrive at 16 steps east, 8 steps north. Do you see the problem? Every destination they reach lies on the same line, forward or backward, longer or shorter, but always on Victor's road. They cannot step off it. They cannot reach a point that lies to the side. Mr. Shadow brought nothing new to the collaboration. His entire journey was already contained within Mr. Victor's. He walked the same road, just more of it, or less of it, or backward on it. He is not a companion, he is a shadow. This is the line of longing. 2 travelers, trapped on a single path, longing to reach the open world but unable to escape the line they share. When one vector is a scalar multiple of another, we say they are linearly dependent. Let v equal the vector 2, 1, and let w equal the vector 6, 3. Notice that w equals 3 times v. The vector w points in the exact same direction as v. It's simply 3 times as long. Now consider all linear combinations. C times v plus d times w. C times v plus d times 3v equals c plus 3d, all multiplied by v. No matter what values c and d take, the result is always some scalar times v. The combination never escapes the line defined by v. The span of 2 dependent vectors is a line, not a plane. Now let us return to Mrs. Willa. She stands at the origin beside Mr. Victor, but unlike Mr. Shadow, she does not look at Victor to decide who she is. She looks at the horizon and chooses her own direction. 2 steps east, 1 step south. It's not opposite to Victor's path. It's not perpendicular. It's simply her own, a direction that belongs to her alone. When Sir Constant transforms Mr. Victor and Dame Della transforms Mrs. Willa, and the 2 travelers combine their journeys, something miraculous happens. Imagine Sir Constant chooses 1 and Dame Della chooses 0. The destination is wherever Mr. Victor alone would go. Now imagine Sir Constant chooses 0 and Dame Della chooses 1. The destination is wherever Mrs. Willa alone would go. Now imagine Sir Constant chooses 1 and Dame Della chooses 1. Mr. Victor walks his path. Then Mrs. Willa continues from where he stopped. The destination is somewhere neither could reach alone. Off Victor's line, off Willa's line. Somewhere new in the open world. Imagine every possible number Sir Constant could choose. Imagine every possible number Dame Della could choose. Positive, negative, large, small, 0, fractions, anything. Where can Mr. Victor and Mrs. Willa reach together? Everywhere. Every single point in the flat, endless world. Name any destination, any point on the plane, and there exist numbers for Sir Constant and Dame Della that will take them there. This is the plane of possibility. It opens only to travelers who walk different roads. It belongs to those who are truly independent. When neither vector is a scalar multiple of the other, we say they are linearly independent. Let v equal the vector 2, 1, and let w equal the vector 2, negative 1. There is no number k such that w equals k times v. If there were, we would need the vector 2, negative 1 to equal k times the vector 2, 1, which equals the vector 2 kk. This requires 2k equals 2, so k equals 1, and k equals negative 1, so k equals negative 1. But k cannot be both 1 and negative 1. No such scalar exists. The vectors are independent. The set of all linear combinations, c times v plus d times w, fills the entire 2-dimensional plane. The span of v and w equals r2. Two independent vectors in two dimensions can reach any point in the plane. This is the fundamental insight. Dependence traps you on a line. Independence opens the plane. Now imagine someone gives Mr. Victor and Mrs. Willa a challenge. A messenger arrives at the origin carrying a sealed letter. Inside is a destination, the point 82. Find your way there, the messenger says. Discover what Sir Constant and Dame Della must choose so that your combined journey ends exactly at this point. Mr. Victor and Mrs. Willa look at each other. They know they can reach anywhere on the plane. But which numbers will take them to this specific destination? This is no longer a question of possibility, it's a question of precision. Imagine Sir Constant chooses the number C. Mr. Victor's journey becomes C times his usual path. 2 C steps east, C steps north. Imagine Dame Della chooses the number D. Mrs. Willa's journey becomes D times her usual path. 2 D steps east, D steps south. Combined, they travel east, 2C plus 2D steps, north, C minus D steps, because Willa goes south, which subtracts from north. The messenger's destination is 8 steps east and 2 steps north, so we need 2C plus 2D equals 8, C minus D equals 2. 2 requirements, 2 unknowns, a puzzle to solve. Finding specific scalars C and D that produce a desired linear combination is equivalent to solving a system of linear equations. We want C times the vector 2, 1 plus D times the vector 2, negative 1 to equal the vector 8, 2. This means the vector 2C plus 2D, C minus D, must equal the vector 8, 2, which gives us two equations. 2C plus 2D equals 8, C minus D equals 2. This is a system of two linear equations in two unknowns. How do Mr. Victor and Mrs. Willa solve this puzzle? They use a method as old as algebra itself, elimination. The idea is simple. If we can remove one unknown from one equation, we can solve for the other. Look at the two requirements. 2C plus 2D equals 8. C minus D equals 2. Imagine we take the second equation and double it. 2C minus 2D equals 4. Now we have 2C plus 2D equals 8. 2C minus 2D equals 4. Watch what happens when we subtract the second from the first. The 2C in both equations cancels out, eliminated. We're left with 2D minus negative 2D equals 8 minus 4. 4D equals 4. D equals 1. Dame Della must choose 1. Now we return to either original equation. Using C minus D equals 2, C minus 1 equals 2, C equals 3. Sir Constant must choose 3. The answer. Sir Constant chooses 3, Dame Della chooses 1. Mr. Victor and Mrs. Willa will arrive exactly at 8, 2. Elimination is the systematic process of removing variables from equations. Starting system. 2C plus 2D equals 8, equation 1. C minus D equals 2, equation 2. Multiply equation 2 by 2. 2C minus 2D equals 4, equation 2 prime. Subtract equation 2 prime from equation 1. 2C plus 2D minus 2C minus 2D equals 8 minus 4. 4D equals 4. D equals 1. Substitute D equals 1 into equation 2. C minus 1 equals 2. C equals 3. Verify the solution. 3 times the vector 2, 1 plus 1 times the vector 2, negative 1, equals the vector 6, 3, plus the vector 2, negative 1, equals the vector 8, 2. Check. The system has exactly one solution. C equals 3, D equals 1. But not every destination can be reached by every pair of travelers. Imagine a darker story. Mr. Victor stands at the origin with his usual direction, 2 steps east, 1 step north. Beside him stands not Mrs. Willa, but Mr. Shadow, the one who copies Victor's path, walking 6 steps east and 3 steps north. A messenger arrives with a new destination, the point 1, 0. 1 step east, 0 steps north. Mr. Victor and Mr. Shadow set out to find the right numbers. Sir Constant will transform Victor. Dame Della will transform Shadow. But something is wrong. No matter what numbers they try, they cannot reach 1, 0. Why? Because 1, 0 does not lie on Victor's line, and Victor's line is the only place they can ever reach together. Mr. Shadow, walking the same direction as Victor, adds nothing. Their combined power is the power of 1. They stand at the origin, staring at a destination they can see but never touch. This is the impossible crossroads, a point that exists in the world but lies forever beyond their reach. The equations have no solution. The system is inconsistent. When vectors are linearly dependent, some destinations become unreachable. Let v equal the vector 2, 1. Let w equal the vector 6, 3. And let b equal the vector 1, 0. We want c times v plus d times w to equal b. C times the vector 2, 1 plus d times the vector 6, 3 equals the vector 1, 0. This gives 2c plus 6d equals 1. C plus 3d equals 0. From the second equation, c equals negative 3d. Substitute into the first. 2 times negative 3d plus 6d equals 1. Negative 6d plus 6d equals 1. 0 equals 1. This is a contradiction. No values of c and d can satisfy both equations. The system is inconsistent. It has no solution. Geometrically, the vector b, which is 1, 0, does not lie on the line spanned by v. Since w equals 3 times v, the span of v and w is just the line through v, and b is not on that line. So far, Mr. Victor and Mrs. Willa have lived in a flat world, a plane stretching infinitely in 2 directions. But imagine a larger world. Imagine Mr. Victor can now walk not just east and north, but also up, into the sky, a 3rd direction. His new identity, 2 steps east, 3 steps north, 1 step up. Mrs. Willa also gains this power. Her path, 1 step east, 1 step north, 0 steps up. She stays on the ground, but she's still herself. Now imagine a 3rd traveler joins them. Her name is Miss Uma. Miss Uma chooses her own direction, 0 steps east, 0 steps north, 4 steps up, straight into the sky. 3 travelers, 3 directions, each one walking a path the others cannot replicate. What can they reach together? Imagine Sir Constant transforms Mr. Victor. Dame Della transforms Mrs. Willa. A 3rd transformer, let's call him Lord Epsilon, transforms Miss Uma. With every possible combination of numbers, where can the 3 travelers go? Everywhere. Not just everywhere on the flat ground, everywhere in the entire 3-dimensional world. Any point in space, east or west, north or south, up or down, can be reached by some collaboration of Victor, Willa, and Uma. This is the realm beyond. Three independent travelers open three-dimensional space. In three-dimensional space, vectors have three components. Let V equal the vector 2, 3, 1. Let W equal the vector 1, 1, 0. Let U equal the vector 0, 0, 4. A linear combination of three vectors uses three scalars, C times V plus D times W plus E times U. If the three vectors are linearly independent, none of them can be written as a combination of the others, then their span fills all of R3. The span of V, W, and U equals R3, three-dimensional space. In general, one vector spans a line. Two independent vectors span a plane. Three independent vectors span three-dimensional space. The pattern continues. In n-dimensional space, you need n independent vectors to span the entire space. But what if Miss Uma never arrived? Imagine Mr. Victor and Mrs. Willa standing in the three-dimensional world, the realm beyond, but alone. Just the two of them. They can still collaborate. Sir Constant can still transform Victor. Dame Della can still transform Willa. They can still combine their journeys, but now their reach is limited. Imagine every possible number for Sir Constant and Dame Della. Imagine every possible collaboration. Where can Victor and Willa reach? Not everywhere. They can reach any point on a flat surface, a plane, that passes through the origin. But they cannot rise above it or sink below it unless their paths naturally take them there. Two travelers in a three-dimensional world can fill a plane, but not the whole space. They are not dependent. They are simply not enough. Two independent vectors in R3 span a plane, not the entire space. Let VE equal the vector 2, 3, 1, and let W equal the vector 1, 1, 0. All linear combinations C times V plus D times W equal the vector 2C plus D, 3C plus D, C plus 0. These combinations fill a two-dimensional plane inside three-dimensional space. To fill R3, we need a third independent vector, one that points out of the plane spanned by V and W. This is why Miss Uma matters. Her vector U equals 0, 0, 4, points straight up out of Victor and Willa's plane. We have reached the end of our first chapter. We've met Mr. Victor and Mrs. Willa, travelers with direction and magnitude. We've met Sir Constant and Dame Della, transformers who stretch, shrink, and reverse. We've seen collaboration, the combining of journeys into linear combinations. We've witnessed the tragedy of Mr. Shadow, trapped on the line of longing because he copied instead of choosing his own path. We've celebrated the triumph of independence, where different directions open the plane of possibility. We've solved puzzles, finding the exact numbers that lead to specific destinations. And we've encountered the impossible crossroads, where no numbers can take us where we want to go. We've even glimpsed the realm beyond, 3 dimensions, where a third traveler opens a whole new world. But questions remain. How do we measure how far a traveler goes? How do we measure the angle between two paths? What happens when we arrange many travelers into a formation, a matrix, and ask them to act together? These questions will be answered, but for now, remember this. Linear algebra begins with vectors and their combinations. Everything else, Matrices, transformations, systems of equations, spaces of every dimension grows from this single seed. Two travelers, two transformers, and a plane of infinite possibility. Summary of Section 1.1. A vector v in Rn has n components. We write v equals the vector v1, v2, and so on up to vn. Scalar multiplication, c times v, multiplies each component by c. Vector addition, v plus w adds corresponding components. Linear combination, c1 times v1 plus c2 times v2, and so on up to ck times vk, combines k vectors using k scalars. Linear dependence. Vectors are dependent if one can be written as a combination of the others. Linear independence. Vectors are independent if no vector is a combination of the others. Span. The set of all linear combinations of a set of vectors. Key results. Two independent vectors in R2 span the entire plane. Two dependent vectors in R2 span only a line. Finding specific coefficients in a linear combination is equivalent to solving a system of linear equations. A system may have exactly one solution, the independent case, no solution, the inconsistent case, or infinitely many solutions, the dependent case with compatible target. End of Section 1.1.